Hello, my name is Sawyer West, and today we will be slicing the Earth in half. Recall in the first video, we determined if two entities above a spherical Earth can see each other given only their distance, their altitudes, and the radius. In the second episode, we found how far above the ground the line of sight was at any given point. To prove the aforementioned mathematics, we implicitly defined a plane that contained these two entities and the core of the Earth, but we never specified what the equation of this plane was. Since a plane describes constant trade-offs in 3 dimensions, we will first discuss constant trade-offs in 2 dimensions. In 2 dimensions, a line describes a trade-off between x and y. At x equals 0, there is an initial displacement of d above the origin. When we increase our x value, we increase our y value by our rise over our run, in this case a over b. So our height equals the proportion of our trade-off times the amount we traded plus our initial displacement d. While describing a line by solving for y lends itself well to intuition, the equation's current form does not generalize well into 3 dimensions. We will first subtract off the right-hand side of the equation to collect terms on the left-hand side. Then we will scale by b, and finally we will define new constants in terms of the old. The resulting equation is known as the standard form of a line. While for a line we track 2 trade-offs and a displacement, for a plane we track 3 trade-offs and a displacement. Since this plane contains 2 entities, P1 and P2, as well as the core of the Earth, we know these points satisfy the equation of the plane. Observe the third equation, derived from the core of the Earth, tells us the displacement term is 0. Thus we can simplify our system to 2 equations with 3 unknowns. Since we have more unknowns than we do equations, there must be an infinite number of solutions. Intuitively, you can think of each equation imposing a constraint, and each unknown providing a degree of freedom. If we had the same amount of constraints as we did degrees of freedom, we would have a unique solution. Let's let c equal 1. If c is 1, we can find an equation for a in terms of b by subtracting bz to the right-hand side and then dividing by x. Furthermore, we can find an equation for b in terms of a by subtracting ax plus z to the right-hand side of the equation and then dividing by y. Observe the algebra to solve for a and b is symmetrical. In other words, the same steps were used to find an equation for both constants. Since our entities, P1 and P2, must satisfy these equations, we can substitute in their components. Now, we can solve for our constants just in terms of our entities. First, we scale by -1, then multiply both sides by the denominators, and then distribute the x terms. Next, we collect the b terms onto the left-hand side of the equation, and the non-b terms onto the right-hand side. Finally, we factor b and divide the remaining terms to the right-hand side. We can find an equation for a in terms of our entities via a symmetrical process. For the sake of brevity, the proof is left as an exercise for the viewer. While we have found a solution for the unknown terms in our equation, we can simplify using determinants. Observe both the numerator and denominators of a and b look like the determinants of a 2x2 matrix. Further observe the denominators of a and b are the determinants of essentially the same matrix. One is just the negative of the other. But what is the determinant of a matrix? The entries of a matrix represent the components of basis vectors. These basis vectors are added together to construct every other vector in the space. In fact, you are already familiar with a basis. That where we have a vector of length 1 in the x direction and a vector of length 1 in the y direction. Consider the vector -3, 3. We travel 3 to the left and 3 up. So this vector is -3 times our x basis plus 3 times our y basis. Suppose we change our basis. This will stretch the vector -3, 3, and every other vector in the space, as we are summing the changed bases in the same exact proportions. Intuitively, we kept the recipe of the vectors the same, but we changed the units of their ingredients. Determinants, illustrated here by the purple area, describe how much space is stretched by a transformation. Here are the determinants which correspond to the numerators and denominators of A and B. We can substitute these matrices into the equation of the plane. Recall from the beginning of the video, we found the displacement equaled 0 and we let c equal 1. Now if we scale by the denominator determinant, the equation looks like the standard form of a plane. You may think this solution is in simplest form, but the left-hand side of this equation is the determinant of the following 3x3 matrix. If we take the transpose of this matrix, that is, if we flip the positions of the components about the main diagonal, our determinant remains the same. Therefore, we have the following equation for our plane. Let's pause and admire what this equation is actually saying. If we take two of our three basis vectors in 3 space and move those onto our entities, then if we move our third basis vector anywhere on the plane which contains the core of the Earth and these two entities, this must squish all of 3 space onto our plane. Thank you for watching. Please like, subscribe, leave a comment, and hit the bell.